Okay, in section 6.3, we need to talk about zero force members. Now there are two common types of zero force members. You might guess from the name that a zero force member is a member in which there are no forces. To see the two different types of these, rather than looking at their definitions first, I think it's easiest if we look at a couple examples. So we're used to the method of joints now. So let's do a simple method of joints problem where I have a truss that looks something like this. It's a box with one diagonal that goes across it. Okay? And I'll label my points here A, B, C, and D. Okay? Now, if I put a load applied at C going in this direction, we're used to solving these problems, and we could figure out that the first thing we need to do is treat it as a rigid body, and we could find the reactions. You know, A is going to have some AY, it's probably going to have some AX, and B is going to have some BY. And we could go around, and once we solve for these reactions, we could then start at A and solve for the forces in each of these members, right? So we could write two equations for two unknowns. You should be used to this by now. If you're not, you need to do some more homework on the method of joints. But rather than doing that, I want us to look at this joint D over here. And let's draw the free body diagram of joint D. So in joint D, we're going to have FDB going down and FCD going to the left, right? Because we always draw our joints in tension when we don't know what they are. But so we have FCD and FDB. And if I sum the forces in the x direction and set that equal to 0, assuming to the right is positive, then what I'm going to get is that negative FCD, because it's going in the negative direction, plus nothing is equal to, so plus 0 is equal to 0. And if I sum the forces in the y direction and say that's equal to 0, I'm also going to get negative FDB plus nothing is equal to 0. Okay? So what we just found is that both FDB and FCD have 0 loads in them, or 0 force. Now, this is our first case. So the first case of a two-force member is when we have a joint with two non-collinear members where no load is applied. Both are zero force members. Okay, so this is kind of definition number one. When you have a joint with two non-collinear members and there's no load applied at the joint, both are zero force members. Now this problem would change, right, if rather than applying the force there, I applied it over here. Now indeed you would see that this is no longer the case, that FCD would now have some load on it. Okay, because now when I did some of the forces in the x, I'd have negative FCD plus whatever my load P is here, and that would no longer. They would still have to all equal 0, but this would be plus P, and it would be possible for FCD to have a non-zero value, right? It would be, in fact, it would just be equal to the P load there. Okay, so that's case one. The second case, let's do a very similar problem. In that last problem we did, we could kind of surmise that really the only important joints here are the ones, or the only important members, excuse me, are these three, because they're really holding the load, right? But what if this joint here, I actually, or this member here, I turned it into 2 and put another member that went like this, okay? Does that make sense? So this would still be A, B, C, and I'm going to add D right here. Okay, we'll still have our load in this direction. So now, what I'd like us to do, we could do the same thing, all right? We'd have to solve for our AY, and solve for our AX, and solve for BY. Instead, though, I want us to look at this joint D right here. So let's draw the free body diagram of D. Okay, so here's my joint D. I'm going to have FDB going down and to the right, and I'm going to have FCD going up and to the left, and they are collinear. And then perpendicular to that, I've got this FDA. Now, it's not important that it's perpendicular, but I have it drawn perpendicular here. Okay. So what I'd like you to do is we're going to do a little bit of a trick here that's going to help us think about this a little bit more straightforward. Right now you can see this is at an angle. Let's go ahead and rotate it so that our X and Y axes are like this. Okay, so now we're kind of looking at the problem. FCD and DB are in the horizontal and FDA is vertical. So now if I write my force summations, I'll have the sum of the forces in the X direction is equal to 0. So I'll have FCD, and I have to say which way is positive, so I'll say that way is positive. So I'll have negative FCD plus FDB equals 0, which tells us, oh, FCD is equal to FDB. And in the Y direction, I'll have the sum of the forces in the Y is equal to 0, with up being positive, and I'll just have negative FDA is equal to 0. And this right here is our second case of a zero force member. So this rule is slightly different. Okay, so this is in a joint with 3 members, two of which are collinear, and where no load is applied. The third member must be a zero force member. And this example shows you that, right? There's no possible value for FDA other than 0 because there's nothing to counteract it at this joint. If FDA was anything other than 0, the joint would start to accelerate down. And you can tell that because both FCD and FDB are in line with each other. Now, it's not important that FDA necessarily needs to be perpendicular. FDA could run someplace over here. It's still true, though. This is still horizontal. So the vertical component of this FDA has nothing to counteract it. So therefore, this has to be equal to 0. Okay? So this page real quickly shows you our 2 cases of zero force members that you need to be cognizant of. All right? I'd encourage you to look through the text and identify zero force members where you can, because it's going to make solving problems much more direct.